everyone, welcome to my channel, and today we have a question which says the pair of electronic configurations representing ground state term 3F2. So we have been given a ground state term and we have four options which are the electronic configurations, and we have to find out the suitable electronic configuration corresponding to this 3F2 ground state term. Now, we very well know that while representing a term symbol, we have the base term, okay, which is represented by L, the total orbital angular momentum quantum number. Then in the superscript we have 2s plus 1, that is the spin multiplicity, and in the subscript we have the j value, that is the L plus s value, that is the spin and orbital angular momentum quantum number. Okay, now from here we very well know that we have certain base symbols or base terms which correspond to the L value. Okay, so if L equal to 0, the base term or the state, that is called a state term also, is S. If L equal to 1, we have P. L equal to 2, we have D. L equal to 3, we have F. L equal to 4, we have G. L equal to 5, we have H. L equal to 6, we have I, and L equal to 7, we have K. Okay, so this you already know. Now, accordingly, from here, we have been given the ground state term, which is F3, 2. So F term belongs to which L value? So F term belongs to L value of 3. So from here very well we can understand the L value is equal to 3. Now if L value is equal to 3 and we have been given a pair of electronic configurations, okay, like P1 D1, S1 D1, since we have a pair of electronic configurations, so we have to understand that it's a combined value. So L1 plus L2, we have two configurations in each pair. So we have L1 plus L2 is equal to L. That is the summation of orbital angular momentum gives us the total orbital angular momentum. So total orbital angular momentum is 3 here, which is the summation of the individual orbital angular momentums, L1 plus L. Now coming to the superscript values. So whatever values we can get from our term symbol, we will accumulate that first. So the superscript is 2s plus 1, which is equal to superscript is 3. That is the multiplicity has been given as 3. So s becomes how much? So s becomes 1. That means the individual spins, that is S1 plus S2 is equal to 1. That is the summation of the individual spins corresponding to each pair of configurations is equal to 1. S1 plus S2 is equal to 1. That means each spin should be half and half. Okay. Now lastly, what we have from our ground state term symbol, we have the value of J. So J has been given as equal to 2. Okay. So J, we know what is J, the summation of L plus S to L minus S. So we have L, which is 3, and we have S, which is 1. Okay, L plus S, that is the total orbital angular momentum quantum number and total spin angular momentum quantum number. So L plus S is total orbital angular momentum quantum number and total spin quantum number. So that is, so L we already know, total L is 3 and total S is 1. Okay, so L plus S to L minus S, that is 3 minus 1. So that comes out to be 4, 3 and 2. So we have three values for J, which is 4, 3 and 2. Now after getting all these three values, the value of L, the value of total S and the value of J. Now we go back to the question and check out the options. So we have P1 D1, S1 D1, then S1 F1, D1 F1, D1 F1. Okay, let's check out what happens with P1 D1. So in the next step, what we are doing, we are basically searching for that electronic configuration that will fit into our ground state term of 3F2. So this is the ground state term of 3F2 and we have these corresponding values of LSJ, and now we are looking and searching for that electronic configuration that will satisfy all the LSJ values and the ground state term 3F2 for that particular electronic configuration. Now our starting point is P1 D1 configuration. So let's see what happens in the P1 D1 configuration. So starting with P1. So we have this +1, 0, -1. That is the orientation numbers. That is the magnetic quantum number. You all know it very well. So we have individual L1 plus L2. The summation of L1 plus L2 should be 3. So for P1 configuration, we have L1 equal to 1, and the electron can occupy any of these positions. So let us say this, there's a single electron and it can occupy any of these positions. So let us suppose this single electron is sitting here, somewhere here. So L1 comes out to be 1 because it's a P1 configuration. Now similarly, if we write something for D1 configuration with 1 electron, okay, so D1 has the magnetic quantum numbers ranging from +2, +1, 0, -1 and -2. Okay, so the electron can sit anywhere. So let's suppose it's sitting here, and the L2 value corresponding to the D1 configuration is 2. Okay, since it's a D1 configuration. So L2, the azimuthal quantum number is 2, and the azimuthal quantum number for P1 is L1. So from here we can see that the summation of L1 plus L2 comes out to be 1 plus 2, that is equal to 3. So our total orbital angular momentum quantum number is satisfied by P1 D1 configuration, that is equal to 3. So I hope you understood this, that how we are getting this conclusion. Now what about the spin value? So S1 plus S2 comes out to be 1. That means the individual spin S1 and S2 are half each. So since we have 1 electrons in P1 and D1, so obviously the spins should be S1 for P1 plus S2 for D1, that is equal to, since both are containing 1 electron each, so half plus half equal to 1. So we got the spin value as well from the P1 D1 configuration. Now coming to the J value. So J value from the ground state term symbol is 2, and we have the possibility of 3 J values, 4, 3 and 2. And now you can see for P1 and D1 configuration that we are discussing currently. So each of these configurations are less than half filled, that is less than half occupied. So that is why we know this rule: whenever this electron is less than half filled in a particular orbital, we have the least value of J. When it is more than half filled, then we have the maximum or the highest J value. So in our case, we have only 1 electron in P and 1 electron in D, both less than half filled. So that is why we have the least value of J, that is 2. So the value of J equal to 2 is also satisfied by the P1 D1 configuration. So we conclude that the P1 D1 configuration corresponds very well with the 3F2 ground state term symbol. So now we have one conclusion, that the P1 D1 electronic configuration satisfies the 3F2 ground state term. Okay, now going back to the question. So we have P1 D1 in option 1 and P1 D1 in option 3 and P1 D1 in option 4. So P1 D1 we have with S1 D1, D1 F1 and S1 F1. So let's try all the remaining 3 electronic configurations one by one, and let's just check that which one satisfies the required ground state term 3F2. Okay, now we check S1 D1. So D1 we already know that it satisfies the 3F2 configuration. But what about S1? Okay, now considering S1. So S1, first of all, we very well know that the L value corresponding to S1 configuration is 0, because the azimuthal quantum number for S is 0. So for S1 configuration, the first thing is the value of L1, that is the azimuthal quantum number, corresponds to 0. Since we have an S orbital, so L1 contribution is 0 for S1 configuration. Now if L1 is 0, then L1 plus L2, we have a pair, that is with S1 we have D1. Okay, D1 combination. So D1 we already checked that it has, if it is L2, then it has 2 value. But the total L is equal to 3. So L1 has to be 1, because the summation of L1 and L2 has to be a total of 3. which is not satisfied for the S1 configuration. So before we move ahead with the other calculations for S1, so in the first step only we know that L1 value of 0 does not satisfy the summation of L1 and L2 equal to 3 for the S1 configurations. So we do not move ahead with the S1 electronic configuration. Okay, then we move to the other combination with P1 D1, that is D1 F1, the third option, D1 F1. Okay, let's see what happens with D1 F1. So D1 already we know D1 satisfies the azimuthal quantum number of 2, and then F1. So if we consider F1 contributing to L1, so what should be the value of L for F orbitals? So L azimuthal quantum number for F is 3. Okay, so for F orbital containing 1 electron, L1 value is 3. Again, for D1 F1 configuration, the L1 plus L2 value, so D1 corresponds to 2, okay, and F1, the L value for F1 corresponds to 3. So if we designate L1 corresponding to F1 equal to 3, then L1 3 plus L2 for D1 is 2, that is equal to 5. But according to our ground state term, we have L1 plus L2 equal to 3. So this combination of D1 and F1, this combination of D1 and F1 also does not satisfy the total orbital angular momentum quantum number value of 3. So D1 and F1 is also striked out from our option. So this D1 F1 cannot satisfy the summation of L1 plus L2 equal to 3. Now what we are left with, the P1 D1 combination. So D1 F1 we checked. Now with P1 D1 we have only one option left, that is S1 F1. Okay, so let's check that quickly. S1 F1. Okay, so S1 F1. Now for S1 the L1 corresponds to 0. For F1, L2 corresponds to 3. So L1 plus L2 is equal to 3. That is our required value of total orbital angular momentum quantum number. Okay, done. So this part is satisfied. Now moving on to the S part. So total spin angular momentum quantum number, S1 plus S2. So each of these S and F orbitals have 1 electrons each. So S1 is half and S2 is also half, corresponding to a value of 1 for the total spin. Okay. Now if total spin is 1, then definitely 2s plus 1 is also equal to 3. That is the multiplicity. And we have the given ground state term as 3f2. So multiplicity is also satisfied because multiplicity here is the superscript 3. Okay. Now coming to the J value. So what about the J value? So J is L plus S to L minus S. Okay, L is 3 here, S is 1 here, and then again 3 minus 1. So here also we get 4, 3, 2, 3 possibilities for J value, and since the S and F, both these orbitals are less than half filled, so the least value of J will be applied for the ground state terms. So obviously the J value for S1 F1 combination is 2. So very perfectly we have the ground state term as 3F2 corresponding to the S1 F1 electronic configuration. So moving back to the question, we have the fourth option P1 D1 and S1 F1 as the matching electronic configuration, which perfectly fits with the ground state term of 3F2. So I hope you understood this. It's a nice and very scoring question. If you have the concepts clear, that what all quantum numbers we require to understand to find out our ground state term. First of all, we require the azimuthal quantum numbers L1, L2 and their summation. And then we require the total orbital angular momentum quantum number, which corresponds to the base term, and then the total spin quantum number corresponding to the number of electrons that is occupying a particular orbital, and finally the J value, which is the L plus S to L minus S. So it ranges from L plus S to L minus S. And then when we know the total L, J, and spin and the spin multiplicity, all of these values, then we can very well understand that what ground state term we have and the corresponding electronic configurations or vice versa. So sometimes electronic configurations are given and you are being asked to identify the ground state term. And now in this question, the ground state term is given and you have to identify the corresponding electronic configurations. So hope you understood this explanation and hope it is clear. And if you have any queries, any topics, subtopics in chemistry which you cannot understand, any problems which you have in chemistry which you cannot solve, so please do write in the comment section. And if my videos are helpful to you, please like, share and subscribe, and please let me know what all doubts you have in chemistry. Thank you so much.